Good morning to all of you. So we have close to about 287 people, no, 290 people online today. Uh, Now today the main focus of our discussion is going to be, I'm going to show you, I think we started showing you the Tantric uh, uh, in the last session. And I'm sure some of you understand. We actually also did uh, take a few exercises, and not. I think you did one or two exercises on Tantri. Today we will do more, but we didn't get down to doing any kernels in the last session. So today we are not going to do too much of conceptual stuff, but I'm going to introduce you to the kernel writing and how do we create a GPU program. Because in the last session, the only kind of program you created was a simple, squares and cubes kind of a program. So today you will do a bit of GPU programming. You will understand how to do GPU programming and basically apply the matmul. We'll start with the matmul, that is matrix multiplication, and then we will do at least a couple of more, if not three more exercises for you to do. And today I'm going to go a little slow. I'm still going a little slow, as you must have seen. Normally, I never use this pace, but it's okay. So you will see at the same pace two or three more programs, which will help you understand the idea of GPU programming and the idea of kernel writing. So that's basically the idea that we are going to focus on, is to familiarize you with the idea of writing kernels in Python and having them executed on a GPU kind of hardware. So it will give you some understanding of how that happens and all that. So given that, I think we will start with the introduction of the program itself. I will not, because the introduction of the program itself will take some time. And I think we have done enough of background in the last 3 or 4 sessions to help you understand what is a naive matrix multiplication, what is a GPU-based matrix multiplication. So I'm going to show you both, and you're going to do both. And we are having a program which actually does both and counts the time taken. And it's a very illustrative program as to why the naive way of doing matrix multiplication is not good, or the sequential way is not good, and how do you get it done parallelly. So today you're going to do it parallelly and see it happen for yourself on our GPUs, so that you get a good hang of how it happens. Uh, uh, so let's start. I think let's walk through the first Jupyter notebook, and we will start doing it. Uh, so we will start with matrix multiplication and illustrate. I'll walk you through first the program. I'll give you the anatomy of a program. As you might have noticed, we have shifted our platform to Google from the other one, and from the GoToWebinar or GoToMeeting. Reason is very simple, that we had got into GoToMeeting or GoToWebinar for more number of people. We discovered, as I have been thinking, that we will not have more than 500. So that is where we are, and I think my reading was correct, that it's very difficult to get more than 500 people to get interested in this kind of technology. Though there is no reason why I shouldn't be seeing more. I think this the students can also do, right?
Yes.
Yeah, I suggest you can also do this on your desktop. So what you need to do is you need to go to the tantric tantric.teleuniv.in.8201, and then 8201. No?
888.
Achha, 888. Sorry, then you will get directed to 8201. So the notebooks are all there in 8201 or whatever. That will depend on your own server. So you need to go to tantric.teleuniv.in.88811. Okay, 88881. Sorry, 88881.
Yeah.
I hope I'll repeat it again.
Please go to aa.telenu.in and log in from that link, Tantric link. Use the Tantric link to go to that page.
Yeah. So you will see something like this on your screen. Okay. Now I'm going to wait here and just check whether at least some of you or most of you are able to get to this screen, because this is going to be the place where we are going to start describing our programs. Uh, uh, I hope you are, so you'll have to say, I think, NB grader and assignments like you did last time. I NB grader assignment list, and you will get something like this. We have already released the practice matmul. What you need to do is you need to fetch it, but prior to that you should see something like that, some what we are seeing on the screen. So I'm just going to pause and ask one or two people, are you able to get to the screen after login? Okay. See, if one or two people are getting, I am fine, because that means the others will soon get it. See, what you have to do is once you log in, you have to go to the NB grader. At the top, you can see the notebook grader. I mentioned this last time, and in that there is an assignment list. Now, I'm not going to repeat again and again, because otherwise we'll be just repeating. Uh, uh, and okay. Yeah, did we enroll the people who were there?
Yeah.
Yeah, we did enroll the people who made mention of that.
Addition of 127.
We have added about 120 more people than last time. So, so that is there. Okay, so now nobody has submitted, and I think we are having about 223 people connected. Yeah. Now what we will do is we will do a fetch on this. So it comes to my machine, not my machine. It doesn't ever come to my machine. It comes to my server, uh, your server at the back end. And then now you have downloaded assignments, and now you have that practice practice matmul. We'll open that practice matmul. We'll just open it, and you'll see it. This is what is the practice. So please get here. Then I will explain the kernel and the rest of the architecture of the program, and some of it I have explained earlier, but I don't mind doing it again because some of you have caught on recently. I will talk about the whole program, and we will start from the main and work our way through this Python program. So, okay. Now again, I'm going to ask you: have you reached this screen? The screen which has import numpy as np, import number from number, import kuda, and all of that. So I'm going to just okay, good. Some of you are there. That means everybody will get there. Okay, wonderful. Okay, now we are getting ready to start and make ourselves understand the first matmul program in Python. So this is the program. I've just made my screen bigger. I'm going to come to the kernel little later. I'm going to first talk about the main program, and then we will come back slowly. Okay. Yeah. No, I think we should start from the main. This is the main. So let me start from here, and explain to you what we are going to do in this program. So I'm going to start line by line and try and illustrate. We are in pen and try and illustrate each of these lines. Okay, we are going to start with this line. This is going to represent the matrices. So there are going to be two matrices, A, B, and they are going to be multiplied, and their answer is going to come into C or something like that. Okay, so this is the matrix A and matrix B. The dimension of matrix A is M into K. That is the dimension of matrix A. And the dimension of matrix B is K into N. That is B. So the answers dimensions are going to be m into n. So those are the basic things. And each one of them, each of these matrix is a 1000 by 1000 matrix. Now, why did I make a big matrix? So that I can show you the difference between the time taken for matrix multiplication on a GPU as against the time taken on a matrix multiplication for a naive matrix multiplication on a regular CPU. You should appreciate the difference, and that settles in the mind only when you take these kind of huge matrices. I'm not saying this is a huge matrix. It's a big matrix, and let us say that, and it's going to be fairly large. So now going by our thing that I'm going to have an M and an N matrix, and each M and an N matrix requires K multiplications. You know the number of multiplications which are required for this? The total number of multiplications required are 1000 into 1000 into 1000. So in order to multiply the whole matrix, we require about a billion operations, right? A billion operations, and we are going to see how these billion operations, how long they will take on a GPU, and how long they are going to take on a CPU, because ultimately these billion operations have to be done. Either they are done in a parallel kind of manner using a GPU, or they are done in a sequential kind of manner using a CPU. So we are going to help you appreciate both today, and that's one of the objectives I want to get there. Okay, let me rub off this thing and start. Okay, now let's see what does this line do. I'm going to go line by line today because I know some of you are new to Python, or some of you are pretending to be new to Python, or some of you will always be new to Python. I hope less number of people in the last category, but here it is. So look at this. NP is numpy. Numpy.random is a library, and randint is a function or a method in that library. And what is it doing? It is saying, I want to generate random numbers from 1 to 10. I think it includes 1 to 9. I think the 10 is not included, but 1 to 9, that is 1 through 9, all 9 number 10 and all 9 numbers have to be generated. And the size of the matrix A has to be m into k, and I'm converting that. Initially it is a random integer, but I'm converting that into float, okay, just so that multiplication becomes easier, or the multiplication becomes bigger, okay. So we are representing the data as float, okay. So though we are generating initially random, we are representing the data as float. So it creates this matrix, fills up this matrix, creates this matrix, fills up this matrix with numbers, and then converts them into float. Same thing is happening into B. So both of these matrices, one is an M into K matrix, the other is a K into N matrix. These are all generated. Okay. Now we are starting to write the code, and look at the code that we are going to write. So start GPU. We are just going to do this. This goes to the time function provided by NumPy, by Python, sorry, and we are taking the time. So this gets me the current time, and down to the millisecond. It knows what is the time right now. And then we are going to do this GPU matrix multiplication, to which we are going to see how this is implemented, but I'll come back to that. But this is the higher level function. So GPU matrix multiplication, A, B are the two matrices which have to be multiplied, and M, K, N are the dimensions of those matrices, and C is going to be the output matrix which needs to be returned. And after that, I'm going to do a N GPU is equal to, again, I'm going to measure the time after the multiplication, this is obviously the time before multiplication, okay, and time after multiplication. So if I subtract these two times, I will roughly get a measure of how much time this multiplication operation took. This is always a very simple way of measuring how much time a particular operation has taken. And I suggest you cultivate the habit of doing this, because in any GPU kind of code, it is always interesting and illustrative to see how much time that operation is taking, just to get a sense of what is the complexity involved. Okay, and then we are going to print the shape. We are not going to print the output matrix, but for some reason we are only going to print the shape, just to say that the matrix is created and proper. We are not really interested, because they're all random values. We're not really interested how C looks like, other than to say that C is M into N matrix. That's all we are interested in. So that C dot shape will get us the dimension and that. So this is how this operation is going to be done. So I'm now going to go into this thing and understand how are we going to conduct a GPU matrix multiplication, where internally or indirectly the kernel will be involved. The matrix kernel will also get involved. So we are going to see how to make that happen. And I think on this part there shouldn't be too much of confusion. We're just measuring time, that's all. Okay. I think now we'll have to rub off this part. And let's go to the GPU matrix multiplication, where you start seeing the beginnings of GPU code. Yeah, no, let's go only to GPU matrix multiplication first. Okay, let's try to get beautiful. So the entire thing is on one screen now, and let me first give you a few minutes, a couple of minutes, to just look at it. See, I always like people to look at code first. I would also like you to make your own thoughts on what perhaps the code is doing. And I always feel that people, once they look at code, they should make their own assumptions. So they don't understand 100% what that code is doing. It's always good to kind of understand what you think it may be doing. It may be correct, it may not be correct, doesn't matter. But you should form your own impression about what that line perhaps may be doing. And as I keep saying, nowadays it has become imperative not to write code, but to actually be able to understand the code which is generated by modern ChatGPT based tools, or your code pilots and all the co-pilots and all that. So it's always good to see. I enjoy seeing and reading good code, whether generated by humans or generated by machine. It's always illustrative, how things are coming together. Okay. Okay. Now, having given you that time, I think it's time to figure out what is happening, and I will spend a little while hoping that you will understand some of this stuff. And let's see. If you understand this whole thing and today's the MATML kernel also, I can tell you, you are in great shape, and you are in you're in good line. Okay, so let me start with explaining what is happening in GPU matrix multiplication. So let's start with this line. What is this line doing? It is creating a C which is empty, which is filled with 0. What is the NP zeros do? It creates a matrix of zeros. Of what dimension? M into N is the dimension of that matrix, which is, as you know, the result matrix of A into B multiplication. And D type, that is the data type, is float 32. Because remember, we have already converted A, B matrices to 32, float 32. And these are the dimensions of A, B. A is M into K, B is K into N, and C is going to be M into N. Okay, so that's what it is. Okay, now let's see what this line is doing. Okay, now now comes a very important point. What is this line doing? Okay, now I just showed you a Python program. Now, where do you think this Python program is running? This Python program, this Python program, or I just showed you the main program a little while back. Just a little while back, I showed you the main program. where is this program running? Meaning, is it running on a CPU or on a GPU? This part of the program, is it running where? CPU or GPU? Okay, I'll wait for 2 or 3 quick answers. What do you think the program which I have talked about so far, where is it running? Okay. Yeah, most of you have it wrong so far, by the way. Okay, yeah. So, so far, all the things that I've shown you, they are running on a CPU. Okay. So, all of the machines on our cluster where these Python notebooks are running, these programs, all of these machines have an architecture like this. They have a CPU, and to the CPU, as a co-processor, a GPU is connected. Every machine which has a GPU already has a CPU also. Very rarely do we have machines which have only GPUs. The machines will have CPUs and also GPU. Part of the computation will be done on a CPU and part of the computation will be done on a GPU. Okay, and GPU has its own memory. I will soon talk about how the GPU memory looks like internally, what is global memory, what is shared memory, what is local memory on a GPU. We'll talk about all of that, but not right away. So at this stage, just understand that the program we have created so far, that's all running on a CPU. Okay. Now, this matrix A, which is created right now, which was created in the main program, and B and C, these are all 3 matrices which are important for our operation. All of these matrices currently are on the CPU of that machine, of your the way I described to you in the last class. All of you are connected to one of the 15 servers, GPU servers that we have in the Tantric cluster. So when you logged in, that time only your destiny was decided. You are dispatched to one GPU server. So, for example, right now, I mean, this may not be 100% correct. There are about 430 people logged in. So out of the 430 odd people, they are all distributed across 15 machines. So each machine, it will not have uniform load, but each machine has an architecture like this, a CPU and a GPU. Okay. Now, the computation for multiplication has to be done on a GPU. So what needs to happen is the matrix A, which is so far on the CPU, has to be transferred to the GPU. The GPU can only act on memory or on data structures which are already on the GPU. The things have to be already on the GPU for us to be able to act on it. So I have to be the first step needed is going to be, I have to transfer this matrix A, from the CPU to the GPU. So this is what this line does. CUDA is the GPU library. To device A is send matrix A to the GPU on the machine, to the default GPU on the machine. Now this also requires sometimes a little bit of fine tuning, because on some of our bigger machines, there is not one CPU, there is not one GPU, there are more than one GPU. And remember, each GPU has thousands of lakhs of cores, thousands of cores. Each one of them has thousands of cores. And each machine may have more than one GPU. Well, the current machines which you are having on the Tantric cluster in this version are all single GPU machines with thousands of cores on each. But some of your seniors, when they are using Tantric, because there we do a little more on training and all that. So there we use machines which have more than one GPU. So this line will look a little different. Here it is going from the CPU to the default GPU, because there is only one GPU on the machine to which your server you are connected to. But you may need one more parameter in this call to decide to which GPU it has to be transferred. So if you don't give that parameter, it is going to go to the default GPU. So it goes to the default GPU. Right now, this stuff is not there, right? In your picture, there is no need. So it has transmitted A to the GPU. Now this line transmits B to the GPU, C to the GPU. Remember, A and B are initialized with random data, which has been converted into float, and C is all zeros or floats. Okay, it's empty, but that's also transferred to the GPU. Now, in the GPU memory, in the GPU shared memory, there is no, it's in the global memory. I'll talk about the GPU memory separately. All three matrices have landed in GPU memory. So they are accessible globally by all the blocks and all that. Now, I'm going to go and explain these 4 lines of code, hopefully to you in a proper way. And then we are going to move on. Okay. So far, what have we done? The main method called ABC, this was all running on the CPU. Now, what it has done is it has transferred A, B, and C from the CPU to the GPU. We have achieved that. Now we are doing something about the blocking structure we are defining the blocking structure so that we can launch the kernel, and we will do that. And we are getting ready to launch the kernels for doing the multiplication, and we will soon start describing that. But let me describe these 4 lines first, and then we will talk about it. So I am going to clean up my screen a bit, and now I'm going to explain these lines. Remember, I told you that the GPU is organized in a grid form. In a grid form, there are thousands of cores of processors. At this stage, I need only I need 1000 into 1000 processors. I need 1000 into 1000. So that is the size of my grid here. So thousands and 1000. Now this is how the grid is. But remember, these are all the processors which are there. I'm drawing it very badly. These are the processors. But I remember telling you that these are the ALUs, or the processing units, GPU processing units, cores as we call it. So now the cores are organized as blocks, remember? And each block has a certain number of cores in it, which is the number of threads. So number of cores, or in our case currently, the number of threads. Okay. This we have explained at length in my earlier videos. Those of you who have a little difficulty getting this, please refer to those videos. They're all there on that KMIT Vista. So here is the blocks, and each block has a certain number of threads or a certain number of cores. If you look at this line, let me explain this line now. Threads per block is 16 by 16. So that means each block has 16 threads and 16 threads. So each block has how many threads or how many cores? 256 cores or 256 threads. So this big matrix which I need for multiplication is consisting of 256 cores, blocks of 256 each block having 256 cores, organized in a 16 by 16 manner. Okay. Now there is a bit of X and Y. So this is the X direction, this is the Y direction. So this is Y, this is X. So let's do a bit of a maths here. So the matrix is what dimension? The matrix total dimension is M and N of the result. Okay. The result has M into N. You think from a C perspective, we have M number of cores here and N number of cores here, organized or broken into blocks of 256 by 256. So how many blocks are required in this direction? How many blocks are required in this direction? How much is this dimension? 16. So how do you go about, and how much is this total size? It is blocks per thread. It is M into N. Achha, this has become N into M, is it? Huh? See, this is blocks per grid. This is X. Okay, this is M, and this is N. Hmm? The X is going in the M direction.
Yes.
So yeah, so M plus, or first look at it. Don't complicate your life too much. M by number of blocks in the X direction. That is this direction, the first dimension. Okay. Let's look at it as the first dimension. So is threads per block 0? So it's, in this case it doesn't matter. So I have to divide M by 16. That will be my basic maths, right? Isn't it? How many blocks will there be in the X direction? What is the dimension in the X direction? This is M. It's taken as this M, and this is taken as N here. So you divide M by number of threads per block 0. So that will give you M by 16. Threads per block in the X direction is 0. That will give you M by 16. Now you'll ask, what is this term doing here? That is to help you do the modulo, because you know, if this is not a multiple, if this is not a multiple, if let's say this is 250 by 16, you will get what? You'll get only this as 15, because this is a remember, an integer division. Remember, in Python this does an integer division. So you'll get 15, and you will have to take care of giving one more block. So you will say threads per, you'll have to take some more in this direction, some more blocks in this direction. That is threads per block 0 is 16. 16 minus 1, that is 15. And then you have to add that and then divide it. So if you have 250, you will have to add 15 to it. Okay, this is the 15 which is getting added. Remember, this is 15. You'll add 15 to it and then divide it so that you get 16. What it means is that though you have 250 dimension in the M direction, you'll have to round it up. This basically doing the round it up. So this is basically doing nothing but rounding up, because when you have to divide it in the threads per block in the X direction, it's going to be whatever the number of blocks in the X direction. In our case, this 16. So it's like doing M plus 16 and doing M plus not 16 but 15, and then doing the numeric computation by 16. So this does the rounding up operation, because I cannot have one block shared between two operations. So a block has to be devoted to a particular set of operations only. So I have to waste that many number of threads, extra threads in that block. So I have to round up. So this is helping me round up. So this is what is happening in the X direction, which is the M direction in this case. This is the number of blocks I need in the Y direction. Okay, that is this direction. Is the same logic. Only thing is I take N and I take another 16. So I measure the number of blocks and again I do rounding up. So this is the rounding up. So these many blocks we need in the X direction. These many blocks we need in the Y direction. So the blocks which are required for the entire grid for doing this multiplication are blocks per grid X, comma, this tuple defines the dimensions of the blocks required in the for doing the grid operation, for doing this multiplication. So for doing this multiplication, I need these many blocks in the X direction and these many blocks in the Y direction. How did I arrive at that? By rounding up the number of blocks. How did I come to each block? Each block I defined the size of each block. Okay, so this is the maths which I have done. So this is the thing which has to be told to the GPU how many, this is a very important parameter for the GPU, that how many blocks per grid are required and how many threads per block are required. But threads per block we have fixed, and on the basis of that we have computed the blocks per grid, because I know my grid is m by n, m in this direction, n in this direction. So my thing is that way, and this is my answer. So you have to adjust your parameters accordingly, and this is an integer division, and we get there. So I hope you have got the sense of these lines, and now I'm going to just talk about one more line, and then we are going to pause a bit to see whether you understood. Now I have two very important parameters with me. The first parameter I have is threads per block, which I am saying 16 by 16 because that's the way I'm going to break it up. Remember, in our given instance of our problem, m is 1000 and n is also 1000. So if you were to do it here, how many blocks will we require in the x direction? Yeah, let's see. Tell us, is cores and threads is the same? Yes. In the present instance, yes. Now, I'm asking a simple question. How many blocks are required in our present case where m is 1000 and n is also 1000? How many blocks will be required? Yeah, I'm waiting for answers. It's rounded up, right? So 1000 by 16, if you round up, 1000 by 16 is what? 16 6 are 96, 42 is 2. That gets rounded up. So 63 would be a correct answer. Am I right? Is everybody convinced that there will be 63 blocks in the x direction and 63 blocks in the y direction? Is everybody convinced about this? Okay. If you are convinced about this, you have already made a lot of progress by figuring out that your number of threads per block is this, and the blocks in the x direction which you need for the present problem where m is 1000 and n is also 1000, we need 63 by 63. Okay. So if we are got that number correct for this, let's travel a little more lines forward and see a little more logic. Okay, now for a we have not yet launched the kernel. That is, we are just defining what each GPU should be doing, what each core should be doing, but we have not really defined what operation it should be doing. That is called the kernel. We have not launched the kernel yet. So now we are going to launch the kernel. Remember, the kernel is going to do, each kernel is going to do only one operation. Remember that, again, I'm going to give you the maths and the logic so that you get it. Remember, our initial matrices are m into k, that is the A matrix, and the n matrix is, B matrix is k into n, B, and our answer is going to be m by n. In this case, the number of columns is n, so it's actually doing it reverse. Actually, it is doing it reverse, no? But actually, we don't care whether it does reverse or otherwise. So you can think of it as this is as n into k. That is the first matrix A. No. I think this is DA, DB, DC. Maybe it won't matter. Okay. Let me not confuse you too much there. Let me clear this. Just a minute. I have to take this. Sorry, we can continue. Yeah, okay. So let me take you through the maths a bit. So we have this is an M into N matrix. Only thing is organized differently. It's still an M into N matrix. So let's not get confused about that. Only thing is we are getting the data organized differently. That shouldn't matter. Okay. So now we are going to do the computation. So this is still an M into K and K into N multiplication. So we are going to so I think I described it last class that the rows of one matrix are going to be multiplied by the columns of the other matrix. This is A, this is B, and we are going to get the result matrix. So each of the kernel is going to take one row and one column. It needs to know information about which row, which column it has to do, and that's it. So a kernel is only going to do this operation, one row, one column. Another kernel, so the answer will be R1, C1, R1, C1. And this second guy here of this will do R1, C2. That is this row with this column, right? This will give us R1, C2 and so on. So this is how the operations are going to happen. If this is how the operations are going to happen, then each operation, each of these operations, which is done by a kernel, is going to be done separately. And how many such operations are going to be done? You know that because each operation requires k multiplications. That's one operation that's going to be done by one kernel. Each kernel is going to operate on one row and one column. That's it. And then we are going to have those operations run by different kernels launched on different threads on different cores. Cores and threads at this stage you can make it synonymous. Okay. Yeah. So yeah, 64 by 64 would also be correct because we are rounding it up. That's fine, but doesn't matter. 63 by 63 is a good thing to go with. Okay, so blocks per grid and blocks per grid Y we have. Now this is what we have got. So let's take this right now as 63, 63. Now this is the most important step in this code. What is this doing? It is launching a kernel. It is launching the kernel, but when it launches the kernel, it needs to know the configuration of the kernel. This is the configuration of the kernel of the operation actually. So this says this will indirectly define how many kernels are going to be launched. Okay, so there are going to be it needs two parameters, blocks per grid, that is it needs this data, that is the blocks per grid in the x direction and blocks per grid in the y direction. Both are captured in this tuple. In Python we call it a tuple of data which contains how many blocks are there in the x direction and y direction and how many threads are there in each block. So in the x direction as well as the y direction, right? How many threads are there per block? So when the kernel has to be launched, when the actual operation has to be launched, we need to know how many blocks are there in the x direction, how many threads are there in every block in the x and y direction, this also in the x and y direction. And then they have to be supplied with the data which has to be already copied into the CUDA, that is on the GPU. So DA is the matrix, DA matrix on the GPU. DB is the B matrix on the GPU. DC is the C matrix on the GPU, and MKN, of course, are the single numbers which are called by values, so no problem, they'll be just copied. They're single values, so number of rows, number of columns, and the number of common. So that is the K operations which need to be done. So this is the launch. This is the launch of the kernel. So the kernel gets launched here. So when it gets launched, what is going to happen? Well, what is going to happen is that we are going to suddenly see a lot of activity where how many threads will be launched? Well, 63 blocks per grid. So many blocks will be launched, and in each block, 256 threads will be launched. So you can imagine that 63 blocks will be launched, and I mean, I'm taking X and Y direction together. And so 63 blocks will be launched, and therefore 63, each block will have about 16 threads. So close to 1,048, I think 1048 threads will be launched. Some of the threads won't do anything. We'll have a check for that because some threads are just extra. They won't be doing anything, but they will be launched. And out of the 1048 threads, about 1,000 threads will be active doing operations because they'll have data. The remaining are launched because of the rounding off operation which took place, all that. So that's the plan. So the thing is, I will now launch the kernel. Now you'll see what matmul kernel is. It's a function which is defined above. We are going to that function. It is launched in this grid fashion, and it will perform an operation. Now, what operation the kernel is going to do, how to create the kernel, I'm going to come to that. So I have not yet described what the kernel is doing. Okay, and I'm now going to tell you what is the meaning of this line. So when the kernel is launched and the kernel is over, that is, all the threads have done their work, and what are we doing? After the threads have done that work, all of that happens here. So when this line comes out, all the kernels have synchronized, all the kernels and threads have finished their work. Each thread on each kernel on one thread on one core, and we have launched so many kernels. And basically, at the end of it, C will be created, one at a time. So each of those 1,000 threads will create one cell of C, and once that is created, we'll have 1,000 cells created. Once that is done, this operation will finish. We'll see how this is done. I'm not yet done with that code. We'll come to that. I have to show you this code. And at the end, what will happen? The C has to be taken back and returned as a result of this operation. So I'll say return DC. DC is what? The CUDA copy, which is still on the CPU, sorry, on the GPU. This has to be copied, and I'll have a reference to it, and I will have to copy it back to the CPU. Remember, because the rest of the code works on CPU. So this does GPU to CPU, all the operations. These operations of the kernel, this line entirely will be executed on the GPU. This is being done on the CPU. All this code is being done on the CPU. The launching of the kernel and all this is where the GPU is involved. I'm going to go to the GPU code and explain to you in a moment. But before you do that, I'm just describing what will you do after the GPU operation is over. Once the GPU operation is over, DC will contain my answer, which I'll have to take it from the memory which is on the GPU and bring it to the CPU. That only can be returned. Then only I can return it. I cannot return just DC. It will be illegal to return GC because I cannot return memory, pointer to a memory which is on the GPU. I have to return it to the CPU. So I have to bring it back, copy to host. Whatever that operation gives me is going to be the memory which is on the CPU, that is going to be sent back. Okay, I hope this makes sense to you. This will come back to you, and this is how the operation will be conducted or done. So the answer is going to come back to the CPU. Okay, now I'm not yet explained this kernel, matmul kernel yet. I'm going to do that in a moment. But before that, I'm going to do my favorite poll just to confirm, have you got all of this, whatever I have talked about? So before that, let me clear the screen. And now I'll create a poll and ask you this question. Have you understood? I have not explained the matmul kernel, please. Barring that, have you understood what needs to be understood? Well, we don't know how it is stored. Why is rounding up necessary? I just told you, we cannot have blocks which are not dedicated to this kernel. We can't have mixed kernel blocks. Yeah, we're just going to ask you. Very simple question is asking. So far, so good. Okay. And it is not good or it is good. So there are only two words. No, we have not launched.
Which slides? Slides.
I am going to explain the matmul kernel. Okay. Well, the threads are not created by us. They are created by the firmware. The CUDA firmware itself will create the threads. We just have to tell it how many threads we need, how many blocks we need, and how many threads per block we need. Rest of it, it will do on its own.
Yeah, to give the poll, please go to that grid icon, select the polls and give your option. Now to go to that grid icon at the right bottom corner and select the polls and give your option.
Well, there is no hard and fast way of determining number of threads. It is your GPU, so you can pretty much define. You could have defined a bigger block or a small block also. You could have said, I want 8 threads per block, and then you could have had more blocks, maybe saved it. But you know, blocks have to be in multiples of threads. Otherwise, you know, you just had some excess. So that will always happen. Blocks per grid. Yeah, I think just wait for my entire matmul kernel to be explained, then we'll see. We are doing rounding up of the number of blocks in each direction. That's why we are adding that 15. I said for now, let's take cores and threads as same. We are not splitting hairs right now. We'll get into the details as we proceed further. All threads are doing exactly the same operation. Only thing is they'll be operating on a different row and different column of the given matrices. All threads will do the same action. You'll see in a moment. The poll is initiated. No, you wanted what clarity? Somebody was asking some clarity before poll. So till now, we should just know the matrices are pointed to GPU and assigning threads and grids. Yes. It can't run. GPUs are not capable of running sequential code, like you know, assigning matrices, doing memory, all that. What is the problem? Blocks per grid. Now 1000 plus 16 by 16 won't be rounding up, no? See, rounding up is to the closest 16 multiple, Baba. That is called rounding up. Okay, let's see the poll. How many people finished? I think people are not able to see the poll or what?
Yes, please go to the bottom right corner. There is a grid icon with which has 9 dots. Click on that and then go to polls and give the poll.
Yeah, it's on that 9 dots. One of those 9 dots you can see on the screen is pointing. In one of those 9 dots, the poll is hiding.
When they log into mobile, they have to go to settings tools.
Mobile they can't do.
Settings tools, the tools they had is off.
Acha, settings tools is where you are allowed to do if you are on mobile. But I hope you are not on mobile, because if you are on mobile, you won't get anything out of this, because soon you have to do it on a Jupyter notebook. I don't like people programming on Jupyter notebook. Okay. Yes, that's correct. 1000 by 16 works as the greatest integer function. That is the intention. That is rounding up, no? Yeah, so far I have about 313 votes. What we'll do is, because there are about 470 odd people, I am going to close the poll maybe at 350 or something. But I need that. I'm asking a very simple question. Have you followed so far? That is, have you followed how did we get blocks per thread in the X direction, blocks per thread in the Y direction? Did you understand what I meant by launch? That's all I'm asking. That's the poll which we have put. And how to go to the poll, we have described how to reach the poll. I'm just waiting for some people to complete the poll so that I can move ahead. Yeah. Okay, I think some of you are not getting to the poll. Threads per block, without knowing the threads per block and the blocks per thread, the MATML kernel will not know totally how many GPU cores have to be created. That's why you need both. It is not 1000 by plus 15 by 16. Well, it is like that, I guess. 1000 plus 15 by 16. It's rounding up. Now you have to decide the block size. Nobody tells you what is the block size. Okay. Now we finished the poll. We are about 2 or 3 points away. If I reach 350, I'll end the poll. If the answer is too much for the GPU, that is, let's say you are multiplying uh, 10,000 by 10,000 and you don't have, no, CPU may have memory to hold, GPU may not. That's a good question, actually. GPU memory is generally smaller than the CPU, but GPU has more cores, but memory we don't know. It can be more or less. But the point is, what happens if you have a very large matrix, let's say 10,000 by 10,000, and you don't have so many cores? Well, in that case, we'll have to break the operation and schedule the operation. You have to use the streaming microprocessor, the SM logic of the GPU. It goes into a little more tricky stuff of GPU. I'll explain. I'll come there in subsequent sessions where I go into GPU programming in more detail, CUDA programming in more detail. I'll tell you what will happen if you have that kind of a situation where the total number of cores are inadequate to handle the operation. Okay. Okay. Now I have taken the poll and looks like most of you are getting it. So I'm going to proceed to show you how the kernel is. In fact, we had looked at the kernel once before. Now I'm showing you the kernel. You see in the same file, there is this kernel with a CUDA JIT thing which says, I need to compile this and send it for execution on the GPU. Acha. Now, this part of the code, as you can see, it is a just-in-time compilation for the GPU kernel. This part of the code is going to entirely run on the GPU. Each GPU, on the GPU, remember there are many cores, and each core has one thread which runs a kernel. Okay. So this kernel is going to run on one core. One core. Okay. Each of these kernels is going to run on one core, and it is going to have to access to these matrices which are anyway copied into GPU memory. These are anyway numbers. So this is the way it is going to have. So now I'm going to illustrate what happens here. Okay, try and understand this piece of code. It is entirely going to be done in GPU. So that's why that CUDA JIT is there on it just in time. So it will compile this, not interpret, which Python does. This will be converted into CUDA code, which is GPU code, CUDA code, GPU code, okay, which is in GPU's own language, which we are not interested in understanding at this stage. If you are with us continuing, probably at some stage we'll get into that also. Now I have this story, row comma column is equal to CUDA grid 2. Remember I told you each kernel works on one row of the first matrix and one column of the second matrix. A is one column, and A is one row, and B is one column. Now it is checking. Remember, sometimes what may happen is, because remember the kernel launched is what? The kernel launched is of a slightly higher, not the kernel launched. The grid which is launched is 63 by 16. Remember? So they are going to be 1048 rows and columns. Sorry, 1048, not rows and columns, 1048 total kernels which are launched. Now, some of the kernels, that is 48 of those kernels, the row and column will not fit in this dimension. They will be those extra kernels which are launched, for which there is no data. They don't have to do anything. They are just spare kernels which are launched without any work. Okay, so they will not do anything, and so that's why this line is important. Okay, now CUDA grid 2, what does it give me? It gives me which row and which column this particular kernel has to work on. That is, which particular row of A and which particular column of B it has to work on. Remember I told you each cell or each kernel is going to work on only one cell of the answer. And to get one cell of the answer, we need to know one row, which row of A and which row of B we are going to operate on, so that we get the answer in C, which cell in C we are going to get the answer for. So in order to do that operation, I have to multiply this and this. So the kernel is going to be launched. How many threads? 1048 threads. Basically 63 blocks, each of 16 threads will be launched. I mean, this is, I'm taking in one dimension, but this is in two dimensions, right? This is in the X dimension and similarly in the Y dimension. So that many. So actually each kernel is 256 and each is 63. These many blocks are there. And each block has so many. So now each operation, each kernel operation has to be done. Each kernel operation needs to know its row and column. And then it has to confirm whether the row is less than M and the column is less than n. For 48 of those, this is not going to apply. Okay, 48 in one direction. Then now look at it. Each guy has to do only one operation, right? So I'm saying temp is equal to 0.0. Now I'm saying because everything has been converted into float. Now for k in range k is the common dimension. That is this and this. This is k. For k in range k, this k is just a variable and this k is the actual thing. What are we doing? Temp is equal to a row k, row of a column, kth column, that is this column, has to be multiplied with this cell here. This has to be multiplied, then this with this. So kth row and column is so and so. So the thing changes that way. Row k, a row k, row stays the same, k changes. Here column changes. Sorry, row changes, column remains the same. This column and row changes k. So that is the range k. So it's going like this and multiplying it with this, and that is getting added into temp. And finally, outside the for loop, this is all happening inside the for loop, and outside the for loop, it is saying C row column. This is the C which was passed to it. Remember, which is a copy. The GPU matrix multiplication will copy it back from the GPU to the host, but this is happening in the GPU only. So C row column is equal to temp. So what did one cell or one thread or one core achieve? One core achieved the multiplication of this row with this column. That is all it achieved. There are k multiplications which need to be done in order to achieve that, and that many additions. Okay, so that k multiplications and additions, every time multiplication addition. So that has to be done. And as I said, additions don't take much, multiplications take the time. So all of that is happening. So each cell is doing k multiplications. This is each thread or each kernel is doing that. And how many such kernels are launched? 1048 in either direction. So 1048 by 1048. That many kernels are launched. 1048 into 1048 kernels are launched. And each is doing one operation, and that operation is this, right? And that's the result we are getting. Okay, now this is what is called GPU programming, where we launch so many threads, and then each thread, what it has to do is defined by the kernel. And each kernel, as you can see, is operating in parallel with so many different kernels. Remember, I told you, I hope everybody has got the maths right. I'll rub off this to focus a little bit on the maths. So how many kernels were launched? 1048 times 1048 kernels were launched. Now, some of the kernels, because of this condition, didn't do anything at all. I hope everybody understood that. And out of this, only 1000 kernels by 1000 kernels, that is, so many operations were launched. And out of this, only these many kernels actually did the work, because these many, and each kernel did this work. And each kernel did how many multiplications? It did 1000 multiplications. Remember, because k is also 1000. We had 1000 into 1000. Each kernel did 1000 multiplications, and in order to get this operation, how many kernels were launched? Potentially 1048 by 1048. How many kernels were active because of this condition? Only 1000 by 1000, because that is the number of kernels which were active. And each kernel did how many operations? 1000 operations. So in short, how many operations happened? 1000 into 1000 operations happened, into 1000 operations happened. But because so many kernels were launched, each kernel did only 1000 operations. So the total time taken, because all of these kernels were launched parallelly, the time taken is only 1000 kernels time. 1000 operations time, because these many kernels were launched. All of these were launched on different cores. Each did their own multiplication separately, and each guy had to do only 1,000 operations. Earlier, each operation would need, each CPU would have to do these many operations, right? To get one thing, it had to do these many operations and get values. So that would have been sequential, right? Now it's all happening parallel, and I hope these are the kernels launched because of our launch thing, which did rounding up. These are active, and each kernel, number of operations in each kernel are these many. Okay. Is this understood? Should we do a poll or no? We can do. Okay. Let's see whether now is this understood. But please, let's have a quick poll, very quick poll. I'm not going to spend more than 2 or 3 minutes on this poll, and after that we are going to do it on the. So we're just creating a quick poll. So far, so good poll. Have you understood kernel? Option A, yes. Option B, no. Please, let's do it very fast. We are launched. I want to finish this in 2 minutes. Because we want to do go to the exercise.
Yeah. Please raise the hands. Thing is there.
Please don't raise hands because we can't respond to hands.
You can give reaction, not a raise hand.
I think that needs a little more. There is substantial needs. Okay, I think we get a message. We will just elaborate some aspects of the kernel again, just so that everybody is on the same page. Okay, we got the feedback. We are stopping the poll. I think, yeah, we'll just elaborate on the kernel a little bit. Now, let me go down a bit. Let me start with the launch of the kernel. It's good that you're giving us feedback. No, go back, go down a little. Okay, now focus your attention on line. Okay, can we get the lines here?
No.
Lines are not there. Yeah.
If you want, I can take this into notepad and.
Okay, no, it doesn't matter. Okay, I think you are seeing the line which is highlighted there. This line. This is for launching the kernel. Okay. Now, matmul kernel is the name of the function. You see, can we just go up a bit? Now we'll have to go out of the edit mode. If you just go up, you will see the name matmul kernel. That's the name of this function. Okay, that's the kernel which is getting launched. So this connects that. Okay, come down. Yeah. Now focus your attention on that line. So which kernel is getting launched? This is the matmul kernel which is getting launched, which you saw at the top. Now there the parameters are only these. Okay, these you don't see as parameters. These are passed in a kind of indirect way. This is a square bracket and a square bracket. This is the launch syntax. See, when a kernel is launched on a GPU, this is launched on a GPU, right? The GPU is going to do that. That's why the data is copied. Before doing that, all this data has gone to the GPU from the CPU, and this is launched on the GPU. Now, for a kernel to be launched, one of the thing is this is called the configuration of the kernel. What does it need? It needs to know how many blocks are there in the entire grid. That is, for doing this multiplication, how many blocks do you require, and how many threads are there per block. So in our case, the blocks per grid, as we know, is 63 into 63. This is the blocks per grid. So this is a 63, 63 tuple. And what is this? This is a 16 by 16 tuple. This is what this tuple is, right? These are the two tuples which define the configuration of the kernel. So it means that how many cores have to be launched totally? The total number of cores launched are going to be 63 into this 16. That is, totally the number of cores, or you take the whole thing. The total number of cores launched are going to be 1048. Now, how did I get 1048? 16 into 63 is 1048. That many kernels are getting launched in the x direction, and in the y direction also 63 into 16, which is 1048, again in the y direction. That many kernels are getting launched. So totally how many kernels are getting launched? 1048 by 1048. How? Because of this line. How many kernels are getting launched? 1048 by 1048. That many kernels are getting launched. I hope now it makes a little more clear. This is how we got to the dimensions of the, so many kernels, that means so many cores are going to be engaged in doing this multiplication, right? So many threads are engaged in doing this multiplication. Now, when that many threads are doing in multiplication, see, some of the threads at the end are there only for rounding up. In any row or in any column, the things, see, it is 1000 by 48 threads are in the x direction, okay, and 1048 in the y direction are getting launched, out of which only let's say 1000, so let's say this 1000 by 1000, okay, my drawing is poor, this is 1000 out of the 1048 and 1000, these 1000 and these 1000 are actually needed because my matrix requires only that many calculations. The size of my matrix is m by n. So there are about 48 threads here and about 48 threads here, which is quite a significant amount of threads in this region, okay, which are wasted. They are not actually even here, right? Okay, these threads are all wasted. These threads are not going to do anything. So there are those 48 of those threads in each direction, which are kind of wasted. So these threads are not going to do anything. Okay. Now this is the launch. So the launch is of a 1048 into 1048 dimension. That many cores are going to get occupied, out of which, and so that many kernels are also going to get launched, because each core is going to do one kernel operation, going to operate on one row of A and one column of B. And then now let's go to matmul kernel. So now the matmul kernel, if you see, line 8 is a very critical line in that kernel. If you see line 8, the line 8 is saying, it's asking the CUDA grid, now you have launched me, now you tell me which row I should operate on, which column should I operate on. Okay, so this line is saying which row you are going to operate on and which column, and this obviously is going to be in the range 1000 by 1000 only, right? No, sorry, this is going to be launched, this is going to be in a range 1048 by 1048, right? This row and column can be anywhere in the range that is in this dimension, because it's asking which thread am I, who am I, which thread am I am dedicated to which row and which column of the answer. I am dedicated to one row and one column, right? So I am dedicated to which row and which column. But this is the line which decides whether this kernel should do anything. If the row and column is on the margins, as I just showed you, they shouldn't be doing anything. They are, those extra threads or extra kernels are being launched because of the rounding up. They are not having work because the matrix is not having work. Okay, no, it is 1048. 16, is it 1008 or 1048? Huh? I thought it is 1048.
Thousands. We are sending 1000. M value as 1000.
No, that we are sending. What is the multiplication? See, I am doing 63 into 16. Oh, sorry. It is not, you are right. Oh, sorry. 1008. Oh, I'm sorry. I was just saying 1048. I stand corrected. It is, I did mistake here. It is 1008. You are right. Okay. So, okay. So, these are 8 extra threads, and these are 8 in either direction, not 48, please. All my 48 stands corrected to 1008, because 63 into 16 is 1008, not 1048. Sorry. Okay. So, so that's what is this. But so actually, I have 1008 by 1008 threads which are active, of which how many do I actually need to be doing work? These are the only threads. So, though these many threads and these many cores are launched, some of them will not do work unless their row number fits in this and column number fits in this, right? Now, hopefully, this line will make sense, right? Yeah. So now temp is, now I am doing, I know which row I am operating on, which column I am operating on, and I have validated this. That means I am in this range, so I should be doing some work. Now, what work should I do? I know which row of A I am going to work with, which column of B I am going to work with. So I'm going to do these K operations. These are the K operations, and fit it in C. Okay, that's all I'm going to do. So I'm going to do one row, one column operation, which means K operations I'm going to do. This is what each kernel is going to do. Each thread is going to operate on only one. Okay. So hopefully now some of it starts making some sense as to what each kernel is doing. How do you launch the kernel? And I stand corrected. It is not 1048. It is 1008. So we have excess about 64 threads, which are excess. Okay. Yeah. I think now we have to show the difference. Yes. Now we'll run it and show. Yeah. Now we are going to show you the execution of this kernel. We'll just do that in a moment. I'm hoping you have kind of understood that. This is very crucial that you understand. Now I'm going to show you the time calculation, but let's run down the page. We have that. Now I'm going to show you something interesting. We are looking at the main. We looked at the main. No, we started there. No?
We started here.
Okay. GPU matrix multiplication we showed you. And now, why are we showing the small thing?
This one.
No, this is only the result. Result we are not interested much. We are going to show the execution. Then we have the 9 multiplication, no, somewhere?
Below. Yes.
Okay. Okay, now we have this notebook. I think you should run this notebook and we'll interpret this result. There is some more code at the bottom which shows the 9 multiplication and times the 9 multiplication also. Okay, since we are looking at that code, we are going to compare how it happens on a GPU and how it happens on a CPU. Okay, now if you see this notebook, we'll just release this notebook to them. No? We have released. Okay, they can see this notebook too. Okay, now I'm just going to go to another part of the notebook, and then we are going to interpret, run it, and interpret the results. This is the 9 matrix multiplication. This is going to be the actual matrix multiplication, and we're going to see at the top the time. This is the 9 matrix multiplication. Again, make C 0. Okay, let's come down without the GPU. How do you do it in class? Nowadays in kindergarten they teach this. So start time, again time. Now you do this multiplication the way you are taught in your maths class. You know, nowadays maths is being taught in 4th class, matrix multiplication. For I in range M, for J in range N, this is how you do an M into N multiplication. For K in, so there are 3 loops. This is the I loop, this is the J loop. This is the number of rows in this, number of columns in this, and for each cell, this is the operation. So in a kernel, this operation is done. This is the only operation done by the kernel. after knowing on which row and which column the I and j are passed, that is the row and the column, and this computation is done. This is done by each kernel. This is not like that. Here it is done all together and we time it. So there is only one core in action here, or a limited number of cores in action here, whereas the code which I showed you, which launches the kernel and does the multiplication, that does it with 1008 cores. So 1000 multiplications done parallelly, 1000 to 1000 multiplications done parallelly, and each multiplication happens very fast. Each cell happens fast. So now look at this timing, and we will run this for you. You can also run, but first let us run it, and we are running this Python notebook.
First select the cell.
Yeah, you have to pick the first cell, or if you run it, I think it runs from the beginning. No?
Yeah, and they have to see the number until unless they should not run the second cells. They are seeing this number. If it is in the process, it will be shown as star.
Yeah. Okay. So first cell is over. Now second cell is over. If you see the number, the cell is completed. Now, see, the calculation got completed. And do we know the time?
The time we will see it in the end.
Now we're just displaying part of the result. Okay.
Now the naive.
Now the naive multiplication will start. We are running this cell.
That is done.
Now the GPU naive is going on.
Running the. It is running.
Now you can see the naive multiplication is running. There is a star there. If those of you are slow, we'll show it again. Right now you can see the star. It's still running the naive multiplication. Remember, it's a 1000 by 1000 matrix. 2000 by 1000 matrix getting multiplied. So see the star. It is still running. It will take a little while. So you shouldn't do such operations. No, we have. If you open this notebook to them, they'll do this. And they'll get locked.
It is open, sir. They
No,
can
but
also.
it will take a lot of time for them.
They can do it parallel.
Still, it is going on. I think some of you must have started. So they must have landed on the same GPU as we did. So that's why we are also taking time.
And if you guys see the library that we have imported, there is no CUDA. It's not on GPU.
This is running entirely on CPU. Naive multiplication. It will take a lot of time because I think we should have shown this without.
3 minutes. 3 minutes. 3 to 3.5 minutes.
No, that will be with you alone. Now with the rest.
Running, so it takes.
Yeah, it's still taking time. That's maybe because it's definitely because you guys have also started, I think, some of you. Anyway, let's watch the circus. Okay, somebody got a result. Good, Ahmeduddin. This is a result we are asking you to post. How much did you get for GPU and how much did you get for CPU? We are still in action. Yeah, our CPU has not completed yet. Somebody completed can tell us. We are looking for computation time on CPU and GPU. Oh, we came there?
No, we are just trying to run.
No, somebody finished. No, let's watch people's numbers. Yeah, you guys run. We are curious to know how much it is taking. Yeah, somebody else got 0.257 for the GPU and one. You can see what order it is different. This was the point we wanted to drive home. What is the time it is taking for the GPU and the time it is taking for the CPU? See, it is not even comparable. You know, yeah, it will take a little while because all of you are banging on together. and it will take a little while because some notebooks will finish, some will not. See, so far as you can see our screen, uh,
There is no score.
there are about 37 people who have finished.
There is no score actually. Actually, that stars are coming.
There's no score.
We didn't have a score because we are giving the complete.
Okay, everybody who finished is getting. Okay, but let's see how are the outputs. Now, please keep posting your outputs so that we know. We have to see their screen.
Ours is also done.
Hmm? Eh,
This is our time.
So our computation came out in our GPU computation happened in 0.2 seconds, and the matrix naive matrix took about 192 seconds. So again, it's almost like 5 times 200, which is about 1,000 times faster. You can see there itself. It's about 1,000 times faster to do it on a GPU compared to a CPU. Are you seeing that kind of 1,000 times different? May not be exact. We'll see the chat. Yeah, we are able to see. Yeah, it is about 1,000 times more. Is it 1,000 times? Yeah.
Yeah, Vishal, just select the cell wise, click on the run button. There is a play button. Select the cell from the top, one after other, and then click run.
Yeah, one after another you run the cell.
Until unless you see the number, just wait.
Yeah. The number means that you have finished that cell. We have finished one, so that's why it's not showing us. If we start running again, it will then show a star, a different number.
Yeah.
A number comes means it is finished. You see that this is finished. This is also, this is going to take time. No.
That will take the time. You will be not seeing number.
Now it's gone into star. So it is taking time. Because this is where the 9 multiplication is happening. I think most of you are getting through. Good. Okay. Now, are you, yeah, you see, it's almost consistently about 1,000 times faster. Even at this point, it is about 1,000 times faster. Okay. I think we will leave you to finish this. And now, I think we can move forward. Okay, I think it's time for a poll. So have you understood the difference between matmul multiplication on naive multiplication and doing it on a GPU? This is an important exercise and a seminal exercise to explain why GPUs are required for AI. This is the core of understanding. Tomorrow in an interview, somebody asks you, why does AI need GPU? You know, I am hoping that you will give a more scientific answer. How would you give that answer? You will say AI is basically based on deep learning. Deep learning requires X input to be multiplied with weights and many such layers and big matrices. So the core of AI is matrix multiplication. The faster you can do matrix multiplication, the better you can run your AI engines. The better you can run your AI engines, the quicker you will get your inference or your understanding. And therefore, for AI to be sustainable, to be doable, to be practical, we require GPUs. Hence, GPUs have become critical. Hence, we require data centers. Remember, in this week, something very fundamental happened in Hyderabad, not in Hyderabad, but in Andhra Pradesh, where Google decided to start its massive AI center, gigawatt AI, as it is called, in Visakhapatnam, Vizag. And that basically is something which you are seeing on the screen now, is the amount of GPU that you need. But GPUs don't come free. GPUs are expensive. And more importantly, GPUs get heated up and GPUs consume a lot of power, a lot of electricity. And for that electricity, we need gigawatts of electricity. And therefore, we need a huge amount of different kind of technology or chips, different kind of material. And therefore, today, the battle for rare earth, why the US and China are fighting is primarily on the rare earth issue. So it's right there in front of you why rare earths are important. Rare earths enable GPU, GPUs enable AI, and AI enables countries, and AI enables jobs. So it's all a very simple matrix which I keep telling people about. And you need to see this in perspective as to what is happening around us. Okay. Yeah, some of you will take longer to execute, depends on which GPU you have handed on. Okay. NPU will come to. I'll talk a length about NPU. Now, the other thing is, now we are going to show you some other kernels. At least I think we should see one more kernel today. It's 11:43:44. So we will show you one more kernel, and for a different kind of a problem. Yeah, we can show now a one-dimensional kernel.
We will show them, but we will not release it.
Why?
That is, we want them to type that.
Achha, they'll type it.
No.
Okay. No, but we are allowed to release the assignment without the code.
Yes, that is there.
It is there.
Yeah.
Something else to release.
Yes.
Okay. So, okay. So we are going to explain the code, but this code you are going to write it down and then do it on your own. Okay. We are not going to help you with the notebook. We will create an empty notebook and give it to you. You take that empty notebook and fill it up. I am going to describe the exercise to you. We have practice matpal is over. No? This is what that.
This is all.
So we are going to open up another exercise, but we will explain the exercise first, and then we'll give you an empty notebook. Okay. Just 2 minutes, and we will start with that.
Night guard.
Hmm?
Night guard.
Okay, this is a simple kernel. I'll explain the code in this in a moment, and then we will talk. Now, I would recommend that you read what is there on your screen. You will get it in your notebook, but this you'll get as an empty notebook. So you'll have to note down the code here and then do it. Okay. Now, okay, the university's night guard, some kind of a scenario. Don't get too lost in the scenario. That's not that crucial. So the university's night guard is monitoring CCTV feeds. Sometimes the footage is too dark and the silhouettes are barely visible. The camera has a special negative mode, and every bright pixel becomes dark in this negative mode. Every bright pixel becomes dark and every dark pixel becomes bright. Okay. So formally, each grayscale value is 0 is black, 255 is white, and gray is in between. So we have a simple operation which is matrix inversion. So you have inversion of x and y is 255 minus ix iy. Okay, it's again a two-dimensional kernel, and what are you going to do this time? Do something very trivial. You are given a row, you are given a column. You have to go to the value which is already there in the row and the column, and you have to invert that value. That is from bright, you have to make it dark, or vice versa. That is not 0, 1, but the value will be from 0 to 2. So in simple words, okay, to give you the picture for some of you who take a little time understanding it, let me just describe the problem to you. You have a matrix again of let's say m into n. This is a matrix, okay, and with that matrix you have each cell. This is a cell of a matrix. There's only one matrix here in this problem. So you have to now create an output of this, which is, if the value here is 120, the value here after the operation is done should become 135. How did you get 135? 255 minus 120 is equal to 135. This is the value you got. So if you have 120, it should become 135. Okay, this should become 135 in the inverted image. So the inverted image will get a row and a column, same way like what we did. What the kernel has to do is it has to just take this value and do 255 minus that value, and then that will be the new value of this cell. Okay, that's all it has to do. Very simple operation, excellent for kernel. If you did it on CPU, what you would have to do? You'd have to do row by row, column by column. You have to traverse this whole thing row by row, column by column. So by the time you are done with this operation, if this was 1000 by 1000, how much time you will take? Each operation, let's say, required I units of time. So you would require 1 million into I units of time. You know, that is what you would require, right? 1 million times I. If each operation, inversion operation, took I units of time, then you would need 10 power 6, because this was 1000 and this was 1000 by 1000 image. You would have to do 10 million, million such operations into I units of time. So you would have to do a million inversions. That would be the time taken. Million into I. With this, what will you do? You launch a million, you launch 1000 kernels into 1000 kernels. So you launch a million kernels. Each kernel has to do only one operation. So you will finish the operation in I units of time instead of 1 million times I units of time, right? You will take that operation in this much time as compared to this much time, right? So okay, we'll take that. Okay. Yeah. So we are doing about a million operations in a CPU operation, and here we are doing about how many? We are doing only let's say we are doing a million operations even here in this kernel, but each kernel is doing only one operation, which is one inversion. So you can see the saving in time. This is CPU and this is GPU. So in GPU we have to do I, okay? And in CPU we have to do a million operations. Okay, so that's what we'll have to do. Are we there? Okay, now I hope you have understood. Here the kernel has to do very little. It has to just invert, check whether its row is correct, column is correct, and do the operation. Okay, the rest of the code will remain by and large same. Only the kernel will change, because it just has to reverse the cell, no computation, and there's only one matrix passed. So let's look at the program once, and the main program, and this you will have to do. Okay, we are just going to tell you, but you'll have to type it in and do it. Okay. Yeah, I think the GPU CPU you are doing is good, but I hope you are concentrating on this also. Okay, now I am going to explain the program. We're just going to walk through the program. You can pretty much take the earlier program and copy it. Okay, let's look at the beginning. No, let's start from the. No, you should give all this, but all these parameters and all you should give, no? This code.
That's right, sir.
It's all boilerplate.
If they want to, if
They
you
should
want them
do
to
only the kernel.
write only this part
Maybe.
and also this part.
Okay.
But if I can reset the exercise and release, shall we limit to this invert image? We'll ask them to write the code for invert image one.
I think we should give them the whole code, and they can do CUDA grid 2.
This one. And up to this.
This we should give, because all this we are creating. This is all synthetic.
Only this part they have.
Only this part they have to write. We have to give it that way.
Okay.
And that also they don't have to write it like this. They can just say R comma C is equal to CUDA dot grid 2, because they want which row, which column, and just check rows and columns. See, you can substitute this code. Okay, so we will give you a notebook with the rest of the code. So here it will have the in image, out image. In image is the input image, out image is the output image, which you have to set one cell of it. Rows is the total number of rows in the image, input and output image. Okay. Now this you have to substitute by R comma C is equal to CUDA dot grid 2. The same thing as earlier. You don't have to do these computations. This will be all done internally. You just do CUDA dot grid 2. This will happen automatically. Then do the sanity check, which you know R rows, C columns. The same sanity check, because we may have launched more kernels, and this is what it is. And each cell you have to reverse the color. So the RGB 255 out image RC is equal to 255 minus in image RC. That's how the out image is built. What part of our out image? Only one cell of the out image is built at one time. Okay, you see there only one row, one column, one cell of the out image is built by one kernel. So you invert image is the kernel. Okay, this you have to write. We'll give you the rest of the code. Okay. And can we do that? Yeah. We'll only give you a blank kernel to write to start with. So you just have to pretty much describe what you have to write. And I hope you understand what is happening. So we will launch that many kernels as much the image requires. And then we will basically also that code will create some image using some random logic, which is not important at this stage. So it will create some kind of an input image and expect you to create an output image which has the same dimensions, that is the same number of rows and columns. Only thing it has to do is it has to do this parallelly through a kernel. So it will launch a kernel of this dimension, and you will see. Okay, now since we are on that code, we'll wait for him to edit the code. But meanwhile, can we go through this screen?
Yeah, you can.
Yeah, while he's editing, let's just walk through the rest of the code. I'll just tell you what is happening here. If you see here, what is it doing? Image is equal to, we'll just see this code. Image is equal to, he's generating a linear space of these many columns. He's generating each row. Yeah, I'm on line 15. So I'm generating a linear space from 0 to 255 of how many values? Columns. How many columns are there? In my image, the number of columns is 384. You can see there at the top. So anyway, I am running a bit out of time. So I'll be a little brisk. So this is the number of columns. This is the number of rows for this thing. So rows is 256 columns. This is the dimensions of the image. Okay. So what am I generating? I hope this line makes sense. Image, I am generating one row of the image. One row of the image consists of 384 values because there are 384 columns. Okay, how do I generate? I say I want a linear generation from 0 to 255. That is, the values will be taken from 0 to 255 and spread over 384 columns. So what it means is 384 integers will be generated whose values are from 0 to 255. The values are from 0 to 255, but the number of values generated are 384. So some values will repeat, doesn't matter, which is fine. Then what are we going to do? Then we are going to create the tiled image, which is take this image which you have generated and repeat it these many rows number of times and one, that is, this is of dimension with this tiling. So what it will do is it will repeat this image these many number of times, these row number of times. So it's like doing this, doing this, doing this. So at the end of it, I will have an image which is 256 by 384. Okay. This says, you can look up this syntax later. This indicates the dimension of the original matrix which I am expanding using this, which I am repeating. So rows one, these many rows, okay, and so the number of rows is these many, and this is the image which is to be repeated in this matrix form. So this is what it will. Now this is not important. You can skip this. This is just doing CPU. It does 255 minus this. Don't worry about it. This is our original image. This is the output image. This is your input image. This is my output image, which is empty. Okay, but its format is the same. That is, it's an output image like zeros. This is 256 into 384. This is your output image, same dimension as input image. And then you see, this is important. What are we doing? We are saying DIN CUDA to device. You see the same thing. This is going to the GPU. Okay. Dout is device. This is another matrix because we don't have zeros. So we are generating this matrix which is like this on Dout, okay, which is also to be copied to the GPU because this DIN Dout are equivalent of input image and output image on the GPU. Okay, and then you have some settings below. Yeah, we can do it after the class also. Yeah, I'm just paused a bit because we are just getting some clarity on how to enable that exercise. Yeah. Now you can see the launch info. Now I'm not going to go too deep into that, but something very similar to what we did earlier. Only thing is it's a slightly different code. TPB is threads per block in the X direction, Y direction. So we are choosing 16 by 16, I think. Huh? What is it? Just go scroll up a bit. We are saying 16 by 16. This is threads per block. We just change the name of the variable. Is calling TPB line 27. Blocks in the X direction, that same rounding up. Blocks in the Y direction, same rounding up. Now we are defining the grid. Again, same blocks in the X direction, blocks in the Y direction. Now these calculations are not important. This is just total number of threads, total number of blocks, all of that. We have to get rid of this. Now comes the place where we are launching the kernel. Okay, just see this. This is the launch of the kernel. Invert image, this is the name of the kernel that which does that 255 minus that value. This is the definition of the grid which is used. The launch, that is how many blocks in the x direction, how many blocks in the y direction, definition of the grid, and definition of a block. So this is a definition of the grid, definition of the block. D in is the input image, D out is the output image, rows is number of rows in the image, columns is the number of columns in the image. So this is the input image, this is the output image. This is the launch of the grid, two-dimensional. See, remember, whenever we launch the grid, we have to indicate how many blocks are there. Blocks are there, and how many blocks are there, and how many threads are there per block. This is needed for the GPU to launch that many number of threads. So it will launch how many threads? Grid in each direction, and number of blocks, number of threads per block. That is what. Now here, there is one more important line which was not called earlier. See, each thread will do its own job. Now what CUDA.synchronize does is, we could have called it last time also, but we didn't. We should call it as a regular habit. CUDA.synchronize waits for all the threads to finish. Because sometimes what happens is, though they are all happening on different GPU cores, some of them may take a little more time, and this line ensures that I'm not going to proceed forward till all the threads which are launched here, because this is going to launch the kernel, this is going to launch so many threads, and each thread is going to do one operation, and we are going to wait for all the threads to finish, and then we are going to copy D out, copy to host, into that out.gpu. Out.gpu is the data structure which is used by the CPU. So this is that going to happen. This is the output image of the answer, and this will be the inverted image. Okay. So this is the operation. Now I have described. Now how does the kernel look like? Also I have described. This is the launching of the kernel. Invert image is the name of the kernel function. This is some display to show the output. Can we go up? You know, I just go up. Yeah. This is the invert image. You remember, this is the name of the kernel. Takes 4 parameters: input image, output image, rows, columns. Now R and C, I told you, you can get it easily by saying R comma C is equal to CUDA.grid2, and then you can do the calculation and do the inversion. So it will happen real fast. I don't know whether we have the timing of that. Do we have the timing?
No.
Okay, we don't have the timing, but you can put the timing and you can check on your own. You know, you can call that function and check where, when you do it on a GPU and a CPU. In a CPU, you'll have to do it one at a time by going through each cell and reversing it. You'll have to do. Okay, and okay. Anyway, I'm not going to help you with that. So you're just going to write a kernel, and we're going to test the kernel. Okay. So I'm getting ready to release this code, release this notebook for you. So here is how I'll release. It's called the night guard exercise. I'm going to get it published. So it will move to the servers, but not to your directories on the server yet. So it's now getting percolated to the 15 GPU servers in our cluster. The publish will do that. Okay. Now on one node it is not published, it's waiting to get published. Some nodes it is yet to be published. So we're trying to publish it on every kernel, every server. Okay, the monitor is saying not running, loading, checking. Oh, this is an interesting screen, guys, for you to understand. If you see on worker node 1, there are 6 people working, so those guys will get their answers fast. And worker node 2, 33, it's a bit loaded. Worker node 3 is 25. Worker node 4 is currently down. We don't know why. And same is the situation with 8. And you see the number of people already active on each. Yeah. And 15 is also down. So this part of our cluster is down for some reason. So there are, I think 4 is coming up. See, worker node, these things are getting published. There's some access issue. It's not down. 3 are down, 11 are up. Yeah, you can see we are waiting for the machines to come up. As a matter of point, this is all our in-house software. So this cluster development has happened all by KMIT's own software company. It's entirely our. Now 4 is up, 8 is up.
Everything is up.
Now everything is up. Now I think we can publish. So we are now sending the exercise to the cluster. First we ensured. Yeah, I think now we will get the published status also.
Published results.
All are published?
Yes.
Okay. So we are now, you are seeing that everything is published. So all are published correctly.
I'm releasing.
Now we have also released them. Now you should be able to see it in your screen. You have to write this one kernel, that's all. Okay. So the night guard exercise, you can now fetch it. We have released it. And you can open it. And now you are only expected to write this inversion of the image code.
And comment this line or remove this line.
Yeah, and remove that raise not implemented error. That is by default comes when we have you when we ask you to write your code. Remove that error. Don't raise that error. You can comment that line or delete that line. Write the invert image and we will see how many of you get it. Yeah, this indicates the load on each of our machines, each of the clusters. So potentially there are about how many students totally? 400 something. No, some people finished.
Once you finish, please submit.
Yeah, once you finish, please submit. Just check a few values whether they are 255 minus that one. Yeah, just a couple of minutes. You please keep submitting. We are just trying to change our grading so that people who write it correctly get it. Yeah, just wait on the validating logic. See, it is saying when I click validate, it's giving me an error. You did not provide a response. So that means for some test cases, the answer is not there. Yeah, something like that should be the output. It's working when we write the function in the cell where your answer here. Yeah, you're supposed to write your answer there only. The test cases will pass, but the problem is that you will not get, I think, 100 marks.
Yeah. Please stop working on that. It's a
Why you have to test it? Really? Yeah, I think we have given you another notebook. Is it?
Yes.
But is that correct?
Yeah.
Okay, we have given you a better notebook. It is called just Night Guard. Okay, just go to that. We have started it. Please put your same answer. Put it in Night Guard, not practice Night Guard. You just have to retype the code with the 2-3 lines. In the Night Guard, it is in assignment list. If you go and see your assignment list, it is under Night Guard, not practice Night Guard, Night Guard. Yeah, the Night Guard, plain Night Guard. Yeah, it will You have a fresh exercise. Hopefully it will go through. And you have to put your answer where your code is here. That's all. And remaining part, you don't have to touch, no?
Yeah. They should remove that line.
Remove that raise not implemented error. Put your kernel there.
Remove this line number 8.
And remove line number 8. Remove line number 8 and put your code there. And let's see whether you are able to evaluate. No other change. I don't know. There are some questions. See, for some reason, I think we are not able to get the evaluation through. We'll do it maybe in the, if it doesn't happen now, we'll probably do it in the next session. I think we need to do a little work on the evaluation. Our test cases are not passing. You may be getting correct result. For example, let me show you a couple of answers which we have got. Okay, these are some of the answers. No, this won't work because there is an error. Let's see some people who have got it right. This looks okay. Yeah, this is okay. This is fine. Only thing is you could have simplified the R and C code by saying CUDA.grid2. But the rest of the code is correct. This is what we were expecting. Just the invert image code. This should have got 100 marks or full marks. Our grading has gone wonky. We'll correct it by next session, and we will be okay. Let's see some more code. This is perfectly okay. Okay. The problem is our grading. Yeah. Let's look at another notebook. Yeah. This is also okay. Let's look at another notebook. This is also okay. Yet another notebook. This is also okay. Only nobody has used CUDA.grid2. You don't have to do these computations. Yeah. Let's see one more. Let's see if our evaluation has. No. So let's see one more notebook. Even this is fine. This is what we expected. We're just expecting you to write the kernel. Maybe we'll see one or two more. Most of you have got it right. No, auto graded also it's not showing up now. It's saying successful, but there's something wrong with your grading, no?
By default, if I put auto grading, there is no point shown. That's the problem. That's why I kept it as manual grading.
But then
And
the
that's
point
why-
is not coming.
Yeah. I'll check it in.
To check it. Okay, the grading, but let's just look at how many people submitted and all that.
134. Submit. 134.
Acha, 134 have submitted. Now some of them may be wrong. Let's pick at random.
That is not written.
If you don't, there is only R and C. There is no calculation of out image. This won't be right. Here also, this is right. This is also right. Yeah, this is what I was expecting. CUDA.grid2 R less. This is easier to write. And let's look at one more. This is also right. Yeah, this is also right. This is not done at all. Just submitted. This is also not submitted. I mean, just submitted without completing. This is correct. See, out of the 134, some of you have done because we are not able to grade you properly. It's okay. Maybe we'll correct it in the next exercise of grading. Okay. So this is what this session was. I think we stretched time a bit. All of that. If I tried RC, oh, it is CR, is it? Rows and columns. Maybe it is that way. Okay.
We are calculating RC in the Volta way, the inverse way one, Y and X. R we have taken for Y, C we have taken for X. That's why we are writing RS.
No. When you do CUDA.grid 2, it has to be CR, not RC, because the reverse will be true. Yeah, you are right, Sadiq. No, we will not check now. In fact, we will correct it and we'll get a revaluation report by the time you come next. Okay, so that keep the grid apart, keep the checking apart. Have you understood what this whole CUDA kernel and all that means? So I mean, that's all we are interested in at this stage. It does not matter some small changes here and there, as long as you have got the big picture. It would have been nice if we could grade you correctly and see, but that's okay too. Yeah, this should be CR, I think, not RC, because it's coming reverse. No, we captured reverse means?
Actually, we should capture an R comma C, but he's captured it as C comma R. And then using that C comma R regular.
No, that means when you do CUDA grid, the C is coming first, R is coming second.
Yes.
No, that is the way we have built our kernel, is like that. That means in the code.
CUDA grid will generally give R comma C directly. But he is capturing R into C and C into R.
No, but he is now doing RC like that only, na?
This lines.
But he is treating rows as rows. First is row, second is row, no? He's not treating it reverse. Our CUDA grid itself is getting reverse. You go to the CUDA invocation, you'll see the issue. No, go down. It's in the invocation. Launch. No, go down. No, the screen is stuck. Convert image. Layout. Rows column. So why is they getting the reverse? His rows should be rows, column should look at out image, na? This is the code which is working. Why is the CUDA grid 2 returning number of columns first and rows?
No. That is returning rows and columns only. But while he is capturing, C stores rows, R stores columns. That way.
No, he's comparing R and the rows only, no? See, the first value returned from grid.
This is inverted now.
Where is it inverted?
Inverted is captured here.
You are saying, this is for the, no, then the output, no, inverted is not that inverted here. It's not, rows are not becoming columns. Inverted is only in values.
So he is.
No, our returning is not correct. The way the grid is getting formed is okay. I think those are issues we'll sort out. Those are not crucial. We'll sort them out. So that's why they are doing this calculation.
Yeah.
Okay, maybe you should go with this calculation only, because that gives you the perfect I and the perfect R and the perfect C. Go with this calculation because this is the way it is, because R is based on Y and C is based on X. It's the problem of the X and Y.
Yeah.
So if you can see here, R, the row is based on Y and X is based on C. Whereas when you say CR, it is correct because what you treat as rows and what it treats as columns is different. So this is why you are getting C row, because if you see the code, it's the same. R is based on Y and C will be based on X. So that's why you have to do the reverse. Okay. In the next session, we will take the more kernels and we'll change our validation also correctly so that you'll get proper answers. So in our next session, we are going to look at more kernels. We'll write about 3 or 4 more kernels, and so that you get a complete grip on kernels and get it to work. Okay. So we will meet next week, and so we call it day to day. Wishing all of you a happy Diwali from the entire KMIT group.